Okay, so let's continue our discussion. So far, we were talking about feed-forward neural network. That is basically a stack of these layers of perceptrons, which we called multi-layer perceptrons. So they have proven very efficient to be used in tabular data. For example, they are heavily used in tasks like fraud detection and recommender systems. So when trained on historical data, often they can outperform even human experts on such tasks. However, one task that remained stubbornly difficult for such machines were image recognition. I mean, even complex multi-layer perceptrons, they fail to match performance that we desire, basically something close to the human level performance. So to understand that, we need to look at the challenges that we have in image recognition. So recall that basically any neural network is basically a way of approximating a function. And by approximating a function, we said that is effectively fitting a curve in among the observed data points. So for example, let's assume a one-dimensional case where we have a one-dimensional X that is coming to our neural network, and we are asking our neural network to return a decision, maybe a 0-1 decision. So maybe X is just a classification problem that we have a bunch of images, image of 1, maybe image of 2, or let's make it more interesting, maybe image of 0 and image of 6, because it can be kind of similar. So let's assume this train of data is coming, and they get some values on X like this. And our neural network is basically has to fit a curve between them. Basically, when it gets 6, we want a decision 6. And when it gets 0, we want a decision 0. So basically, we have 2 decisions here. So here, we are asking our neural network to basically fit a curve here, right? So something like this. So if we had a one-dimensional data space, we could fill it up very quickly with observed data, right? So for example, let's assume we have in our problem, if we had a 1D space, we could fill it up with non-data points, right? So if this 1D goes to 2D, we need exponentially more data. So maybe 9 raised to 2. And if we have ND, we are looking at 9 raised to n. So what does this mean when we are dealing with image? So for example, if our image is a 32 by 32 pixel, right? In this case, and even if we have like RGB channel, 3 channel, here in this case, we are looking at 3072, or in the same analogy here, n is 3072, so we want 9 raised to 3072 data points to have sufficiently filled up space for our neural network to fit the curve. This is a large number, I mean astronomically large. So that's why no matter how smart we train our neural network or our MLP with architecture like that and such inductive bias, we will always struggle. So for example, in a CFAR 10 data set, the best that I've seen that we can do is an accuracy of 74%. And if you compare this to human level, which is 99%, it's very, very far. So, okay, so let me show you another reason. Basically, like I said, if we what we have done so far with MLP and basically classification of images, like the MNIST data. We flatten the image or pixels into a vector. For example, in a 32 by 32 image. And if we flatten this and we give it to the MLP, it can give us a pretty good result when we expect one to be here. It will be always here. It will not be here, for example. So, and the MNIST data is basically prepared like that initially by LeCun and his team to be like that. But what does this mean? This means basically if we shuffle the pixels and we send the same flattened vector to the MLP, it's just basically order has changed and the MLP can still do the classification. And in other words, if we send an input, which looks like completely noisy image, and give it to the neural network, it can tell you with high confidence that this is, for example, number 3. I mean, let's ask ourselves what we are expecting MLP to do and compare it to what we are doing as humans. So the reason humans are able to see is because our brain have a lot of information and knowledge about the world. It has some expectation, some regularity that works like a structure. And this structure basically makes it easy for us to look at an image and screen the image for features and then put together these features and then decide what is inside this image. So the idea here is let's give some insight, some structure to the neural network and make the job easier for it. So let's infuse some of this structure that we know, and we can provide that to the neural network, and then design a neural network with such inductive bias. So 2 principles that we can consider. So first principle, spatial locality. The neural network, that when it's looking at a pixel, consider that this pixel is not alone and it has some local neighborhood and the pattern that comes from this neighborhood. We are not expecting that there is a relationship between this pixel and some very distant pixel. The second principle is if you see the same feature here or here, for example, it's the same feature. So if there's an edge, for example, or a whisker of a cat, it's still whisker. So in your next level of reasoning, you can use the same feature same way. So if we have a feature extractor that is working over this local neighborhood, the same feature extractor can work here. So what does that mean? That means that if I have a neural network that is looking at this and take this as an input and gives out the features, the same neural network basically should work here too. So we don't want to train another one. It's basically the same neural network that we are moving or screening the image with, sweeping the image with. And it works the same. It's the same with the same parameters that looks at this patches of image and gives out the features. So what did I say? I said, basically, this can give us a strategy instead of one very large, massive network that is looking at the image at its entirety. What if we use a very small neural network that analyze one small patch of the image at a time, and we slide it across the entire image to find those features everywhere. The idea is not really novel here. Basically, what we are saying is something that we have done previously in computer vision. And back then, And before heavy use of neural network, what did we do in computer vision was some form of filters that is looking at these patches and give us the feature. These filters were engineered. So the good thing about this filters, that also called kernels, are basically they are interpretable, right? We know what they are doing, what they are looking for. However, they have a limited expressiveness. They can only detect a simple predefined pattern that they are designed for. We have to make a decision which filters or kernels to use. So we said we are looking at basically sweeping a function, a filter, a kernel across the data. And this kernel will give us some form of information that we can use as a feature, right? So as we said, we are looking at a function that slides over the values of data. I mean, for example, in the case of images, we are sliding over the patches of data. In a case of maybe much simpler situation, when we have a train of data points coming, basically in a time series, we can look at some local windowing operation. For example, at each window of length 3, we can get a value that is a smooth version of these 3 data points. And this is basically a kernel of the shape, right? Basically what it does, it adds up all of these values within that window. So this was the moving average that we do. And probably in daily life, if you are a time series analyst. And this is an example that is very common. And it does, what it does is a local operation. And a kernel that slides through each one of these points. So for example, next window will be here, right? And so on and so forth. We can start from here for the first one, and then window moves here, then here, then goes like this. And I mean, if you heard of the term cross-correlation, this is some form of cross-correlation, right? Basically, we cross-correlate all of these windows with the kernel, using this kernel. If we do the same thing from 1D to 2D, this corresponds to what we do as image blurring. So same process, we define a small window and a kernel, and this kernel has some weights. So we have to choose this kernel. We can do the same uniform weight kernel, for example. They sum up to 1, and basically we place the kernel over each patch of this input image, perform an element-wise multiplication between the kernel's weights and the corresponding pixel values in that patch. Then we sum up all the values and all the results of that multiplication to get a single new pixel value. And then we slide the window across the entire image and repeat the same process. For every location, we create a new blurred image, right? So we can do more than image blurring. For example, we can do edge detection and even sharpening of those edges. And for example, in the edge detection, a famous filter is Sobel filter that has both positive and negative values, again, sums up to 0. And it slides over a flat uniform region, and the output will be 0 in that case. But if it slides over an edge, a sharp change in pixel values, the sum of the products becomes larger in positive or negative ways. And this highlights the edge, right? Because the value will increase. So if we want to formalize this in a mathematical way, basically for an pixel of in I and j, we sum up a pointwise operation between the filter at A and B and pixel value at X. And basically, since we are sliding through the pixel values, here in 2D situation, we have both axes, X and Y, which here I use the index A and B, so basically we have a sum of. This operation is known. We call this cross-correlation. And H is the output of this feature map. So, like I said, mathematically this is cross-correlation, although because we are cool, we are calling it convolution. In pure math, convolution really involves a flipping of the kernel first. But since later we will discuss the case that what if we don't know V and we want to learn it, really flipping the value doesn't really matter in that case because it's done by itself. So it will be convolution at the end. So basically what we are saying is, instead of using this handcrafted kernels that computer vision's expert design for us, and each one of them works for a specific feature, we want to continue the same paradigm in the that we have in the course. We want to learn these features, and like I said, in an end-to-end way, features that are working for the task that we want, and they are optimal for that task. We don't want to go learn the domain of computer vision and all of these kernels, and then develop skill on how to make these trade-offs and make these decisions to basically use this dictionary of fixed kernel. And instead, we want deep learning to do all of that for us, learn the kernels, and these kernels are actually optimized for the specific task that we have. Cross-correlation or sweeping function that learns these features in each one of these patches of the window has a nice property that is called translation equivariance. If you shift the input, for example, if you have an image of a cat here, if you move this to somewhere else in the image, it's the same thing, and we want the neural network to not use extra learning capacity for that. In other words, we have the same neural network that learns this kernel, works here and here. And that sharing of weights across all of this position give us a parameter efficiency that later help us in such high dimensional space, because we really reduce the dimension significantly by doing this. So then next we will talk about how we can build such a neural network that we are going to call convolutional neural network. So before applying these concepts to build our first convolutional neural network, let's review a couple of things. First, how we are using this kernel on this image data, and things that we should consider in the implementation. So for example, here, this is an image from the book. If we have a kernel like this and an image here, a 3x3 image, or maybe a patch, but let's assume the image is like this. And now we want to do the convolution or the cross-correlation operation using this kernel. So here we have this 2x2 kernel, and we are going to start from this part of the image. We do the element-wise cross-correlation operation, and this will give us the first output here, which will be 19. If we continue doing this for the next part of the image, we'll get 25, and so on and so forth. So we will see the output of this operation here will be a 2x2 output, which is smaller in dimension than the original input. And if we continue doing these steps, we will end up in the next step with only one output. So what is the problem here is sometimes we need more layers in our operation, in our convolutional neural network, and this operation will reduce the size of the dimension of the data. So to fix this, a very simple trick is to pad the data with this zeros here. And basically what it does is to, in this case of 2 by 2, we can now have an output corresponding to this edge cases on the periphery of the image. And this way, we will retain the same dimension in the output. So keeping aside this problem of reduction of dimension using padding, sometimes we actually want to reduce the dimension. And if we want to do it, we will use strides. So basically, stride is the number of rows and columns that we traverse per slide. So far, we use the strides of 1, but we can change that. And we can also change it for heights and widths. So for example, here, this is figure 733 in the book. If we do the stride of 3 for height and 2 for the width, for example, in the first one, we have this, and the component-wise, we will get that. But next stride will be 2 in the width, so we have this multiplied by this, and we will get that. And for the height, we go 3, we slide this 3 times, and we will get this, which multiplied by the kernel will give us 6. And of course, for the other component, if you do it, you will get 8. So this way we can reduce the dimension if we desire, and while we are controlling for it. The next component that we will use in constructing our CNNs is pooling. Basically, pooling means that we ask a question from the learned features. And this question is a global question, meaning that does this image contain a certain feature or a certain object? We want this question to be sensitive to the entire input. So we need to aggregate this local information gradually, and this way we can get coarser and coarser maps, and ultimately learning a global representation. So we want to do this in a way that we keep all of these advantages that we collect in these intermediate layers. And while we are going deeper in the network, we see more and more of these localities, and our receptive field relative to this initial input will increase. So, and also, if you remember, we wanted our representation to be invariant to translation. And so far, what we did with the cross-correlation was pretty local. We were sliding the window, and we performed cross-correlation during each one of these strides. And now we want to come up with another step that basically inject this invariance to translation. And pooling is doing that for us. We have 2 ways of doing this process, this pooling step. Most common way of pooling. One is max pooling, and the other one is average pooling. And max pooling, basically what it does is it finds the strongest clue, and the intuition is basically each one of these smaller cross-correlation steps that we are doing is like a detective that is zooming into these smaller patches. And then after aggregating all of them, it returns the strongest evidence that it finds. That's max pooling. Another way of doing this is doing average pooling, which is basically to average out all of this evidence that it finds, this detective that we have. And at the end, it gives us a smooth, more general summary of those features that it finds. So usually you will see that we go with max pooling because of this sharper aggregation that it has. But of course, all of this, both of these methods are providing this translation invariance that is the key for us for the image data. So we are going to use all of these principles and these tools in building our CNNs. So we will review the history of these CNN architectures. And the reason is, as you saw, basically what CNN does is it starts from some early layers that learns features that can be generic, and with the intermediate layer, we will aggregate these generic features to build up larger parts of the images. For example, textures, patterns, eyes, wheels, and leaves. So you may ask yourself, well, can I use these features that I learn from some other network even in my own network without training those early layers for the task that I'm interested in? So for instance, if we have a network that is trained on a very, very large data set, which requires a lot of training and a lot of resources, for example, a data set like ImageNet that has 1,000 classes like dog, car, chair, and so on and so forth, the ability of this CNN that basically detects edges, textures, shapes, and eventually objects can be reused in another neural network. And we can freeze that early layers, and we don't need to really train that part, and then add more layer after that to process these features in a way that we want for the specific task that we are interested in. So this is known as transfer learning, that justifies training a very, very good architectures as some sort of pre-trained network that can be used elsewhere. So usually what we do is we split the model, the CNN model, in two parts. One is the convolutional base, which is basically these early layers that we discussed, that they do the feature extraction. And then we have a head at the end that aggregate this final aggregated features that basically use them. It can be even a linear MLP that uses these features just like a regression that uses the feature and make a decision on, for example, if this is a cat or dog, while we are using this convolutional base that can do much more than just detecting cat and dog. But for some reason, you're only interested in this final task, and you can use this over-engineered convolutional base that can give you your cat and dog detection with very high confidence, while you haven't really done any of that training and somebody else did it with a very advanced state-of-the-art CNN base. So it's enough to just replace the head, and with a few shot training in your own data set, for example, you can train that part, this classification head, while you're not touching the base. This basically justifies training very good convolutional bases. And we will talk about some famous convolutional bases that we can use in our own tasks, and we can just basically take them, and without training, we just need to train some classification head at the end, and that doesn't really require a lot of training and a lot of data.